Hi, in this video, I'll be talking about the notion of derivatives in the context of multivariable functions. Before that, we'll start with understanding what is a partial derivative. And you can think of partial derivative as keeping one of the variable constant and differentiating with respect to x or y only. So delta f over delta x equals to the limit as h approaches 0 of fx plus h, comma y minus fx comma y over h. And you can see this looks exactly like how you will write it for one variable case, where in usual sense, it will be written as fx plus h minus fx over h. But now you have two variables, but it's the same understanding in a sense that now you say that you keep y constant. And if you were to differentiate with respect to y, then you're keeping x constant. Geometrically, it means that if you have a surface and you cut the surface with a plane parallel to the x or y axis and draw its curve, then you're basically finding the tangential gradient at that point. And you can extend this to three variables now, and it'll be similar. Also, you can now take, when you have two variables and you take the partial derivative of its partial fx, then now you get two more, because you can partial derivative this with respect to x or y, so you get either fxx or fxy. And similarly for fy, you can get fyy or fyx. And we use the notation as follows. So fxy means that we differentiate with respect to x first, then y. So I hope this part is clear about what is a partial derivative. It is basically can be reduced to your single derivative, where you just differentiate with respect to the variable that you are varying and keeping all else constant. So we take a look at this example where x cubed plus y cubed plus z cubed plus 6xyz equals to 1. When we take the partial derivative with respect to x, we are differentiating this x, so this becomes 3x squared. Y in this case is a constant, and so it gets deleted because the derivative of a constant is always 0. For x cubed, it becomes 3z squared times zz dx. And this part, you can just use the product rule as follows. And by expanding this out and simplifying it, you are able to get delta partial z over partial x equals to minus x squared plus 2yz over z squared plus 2xy. Similarly, you can do so for delta partial z over partial y. So really do practice a lot, then you get familiarized with yourself with writing the notation of partial x over partial z or whatever. And you can really find a lot of examples in the textbook by Thomas Calculus. An important theorem in multivariable calculus is that if you know that your second derivative function of fxy and fyx are continuous, then they will be equal as well. And you can extend this to showing that any permutation of any number of variables, as long as you have the same number of variables occurring, they will be equal. So we just need to prove this for the 2 times derivative, the second order derivative. And really, you're using just the concept of the mean value theorem in the single variable case. And so if you fix x and you are given this function in y, then applying the mean value theorem, you get that fxy minus fay minus fxb minus fab, this is the function, will equals to some derivative times y minus b. And then we can now apply the mean value theorem to the partial of y, and we'll get fxy minus fx fay minus fxb minus fab will equal to the partial derivative times x minus a comma y minus b. So what does it mean is that you first use the partial derivative to get this times y minus b. Then you use the partial derivative again for this fy to get with respect to x in this case, because now you can see that this y part is constant, so you just want to vary the x part, so you get this following. And because of that, we can rewrite the expression as fxy minus fxb minus fab minus fay minus fab. And applying the mean value theorem, now with respect to x, you get the same conclusion. And what you see is that because fxy and fyx are continuous, when you take the limits as xy approaches ab, this part gets removed and we are left with fxy equals to fyx. And so we are done. I hope this is clear, but in most cases you really want to be seeing the proof once, understanding it, and then most of the time you'll be just using this theorem directly. And with that notion, we come to now total derivative of a function. And the total derivative of a real value multivariable function is that instead of finding a limiting value, you find a linear map. And really, why is that so? It's because now that you have two variables, your graph will be like some surface. And so you can't say that, you can still say a line is tangential to this surface, but you have many lines like that. And so what we really want to take note is that the tangential plane is unique. So this plane is actually spanned by any two vectors or any two lines within this plane. And now you can really relate this tangential plane to what we have studied about partial derivative. Because they are spanned by the two partial derivatives in xy, then you get the following equation of the plane. So this is your partial x and your partial y spanning it. And then if it doesn't pass through origin, then it passes through z0 I mean. And this is the equation of the tangent plane. And because of this equation, you can find the total derivative of this, because you can now shift everything here to the other side and divide throughout by square root h squared plus z squared, k squared. And you see that the linear map that we want is actually this portion over here, because this is the FAB over here. So it should be clear that the linear map, it will be just given by the span of the partials x and the partial y. And so really with that, when you want to show that something is differentiable, you can actually just find the partial x and partial y first, and the linear map has to be equals to that sum, that this linear function. And as a result, you can plug that linear function into this definition and check whether this limit equals to 0. But sometimes we just want to reformulate this definition in an easier to use manner to help us prove results. And one way is to say that z is differentiable if the change of z can be of the form this. And this form is saying this form is just saying your tangential plane, how it changes. So the change will be, of course, you have the linear map spanned by your two partials, and then you have some error term. And these error terms must go to 0 as the change in x and the change in y goes to 0. And when this is so, we say that f is also differentiable. And you can actually show the equivalence between the two definitions that we have stated quite easily, and I'll leave it to you. But what we like to note is that if we know that f is differentiable in one variable, then f prime a exists. But this may not be true for multivariable, and the existence of partial derivative won't imply that this will still hold true. And we actually need something stronger, and that the partials need to be continuous. And the reason for that is because when you have continuity, then you are able to apply the mean value theorem to get the following result that allows you to lead you to the conclusion that the change in z actually goes to 0. And so we need the condition that the partials are also continuous in order to conclude that f is differentiable. And so you can find examples where even though f is differentiable, the partials do not exist. The partials, even though the partials exist, f might not be differentiable. Of course, if f is differentiable, you know that this linear map exists, and so the partials also will exist. But if the partials exist and are not continuous, then you are able to find functions that are not differentiable. So you really need it to be continuous and existing for f to be differentiable. And while f is differentiable and the partials exist, the partials need not be continuous also. So you can use this example to check that the partials are not continuous. Lastly, we shall end off this video by stating some properties of the derivative, where the proofs of this can be found in the analysis video, so I'll leave it to you. And that's really just saying that the sum rule apply, the scalar multiplication rule apply, the product rule apply, and it's exactly the same as what you have in your one variable case. And what we like to note now is that if your f is differentiable, then you know that f is continuous. And the reason for that is because if we write our change in z equals to the following, then because we know that f is differentiable, this portion over here will equals to fx naught comma y naught, as change in x and change in y goes to 0. And so this whole expression here will equals to 0, will approach 0 as xy approaches 0. And hence fx naught plus the change in x comma y naught plus the change in y must equals to fx naught comma y naught, as change in x and change in y goes to 0. And so this shows that the function is continuous. Hence, we can state that differentiability implies continuity. I hope you have enjoyed this video. In the next video, I'll be talking about the chain rule and the applications of differentiability. So do catch out for the next video. Thank you.